All right, guys, welcome back. So we left off last time talking about clustered bar graphs, or they call them clustered, or yeah, clustered bar graphs, where you basically have multiple categories, and within each category you have subcategories. So my example that I chose here was so different schools were the categories, and the subcategories were non-STEM versus STEM students, and how much each one had. You could just as easily say what?
Those are some fancy schools.
They're just the first ones that came to mind. I mean, UW for obvious reasons, but I wanted to choose one. Like, since I decided to use STEM versus non-STEM, I figured I'd choose also Juilliard just because that one is primarily non-STEM. So I don't even know if you can get a STEM degree from Juilliard. They're mainly music and and the arts. So I doubt there is, but suspension of disbelief. So like another thing would be like, instead of non-STEM versus STEM, like we could have each cluster, like each category have three things, based on gender, so male, female, other, or non-binary. You could do a lot of different things. You could do it based off like we did cell phone batteries just a second ago, but instead of each category being a different phone, it could be like a different company, and then within the company there's different phone brands. So like the Pixel versus the Pixel 2 for Google, and then the iPhone 14 versus the iPhone 15 versus the iPhone 50, whatever, like the iPhone 95, whatever they have. So that's a situation where you want a clustered bar graph, where you have categories with subcategories in them. And so we made this graph, but we didn't get to actually answer the questions from it. So just some standard questions. Part A would be, which school has the most non-STEM students? Which, I mean, I know it's very apparent from the graph, but it's important to be able to read between the things. STEM is in solid, or is completely white, whereas non-STEM is dashed. So we're looking for the one with the largest dashed bar graph, which would be Juilliard. Part B is, how many freshmen attended Brown this year? So notice this is how many freshmen. So they're broken up into two groups. Non-STEM. Oh, yes. Yes. Yeah, of course. So how many freshmen attended Brown? Not just STEM and non-STEM, but that's completely breaking them up into two categories. There's not like an other category. I guess you could technically have undeclared as an option, but I think undeclared would fall under STEM, non-STEM. So just based on purely this split up of the data. So instead of just looking for the number, we have to add these two numbers. So that's going to be 3,000 3,000 STEM plus 3,500. Okay, thank you. So 6,500 students. And I promise you, on your homework and your quizzes, the graphs will be very, very abundantly clear where the lines are, or they'll list it what the top number is. So because like we just talked about putting an average estimate of where 3,500 would be, but on the exam or on quizzes, it will show up as exact numbers. And then one last question from this section, this thing, is how many more STEM declaring students? How many more STEM declaring freshmen attended UW this year in comparison to non-STEM? Right out of room. That says at the end, in comparison to non-STEM. Sorry. How many more students were STEM at UW in comparison to non-STEM? And so this would be taking the difference between the two things. You have the total number of students that were STEM and the students that were non-STEM. If I wanted to have the total number of students, I'd add those together. But if I want to know the difference between them, like how many more freshmen were STEM declaring, I would take the difference. So I'd take the 3,500 STEM students and I'd subtract off the 2,000 non-STEM to tell me that there were 1,500 more STEM students. That's where we would use a clustered bar graph when we're trying to compare subcategories within categories. And so I think I mentioned it for my last class, but I don't think I mentioned it here. So your homework, one of the things that you'll see in your homework or questions about for this section are things about what type of graph would be best used or what type of chart would be best used. So that is something to keep in mind. That's why I've been giving you examples of when you would want to use something over the other thing. So this would be a situation where you'd want to have categories with subcategories within them. The next topic, the next type of chart that we know about are histograms. The histograms are a specialized bar graph not barred graph, a bar graph, where the categories are continuous, are quote unquote continuous, i.e., related to each other. So an example of this type of thing, of where you want to use a histogram, might be a percentage of people who voted in each age group. That might be a good example of a histogram situation because all the things are continuous. Like you have the 18 to 25-year-old, the 25 to 40-year-old or whatever, and you break it down based on those little age group age gaps to figure out how many people are voting, like what percentage of that age group is voting each year. And probably another example would be like rainfall every year in a certain area, because all of those things are connected to each other. Each year is connected by that concept. So, and then just as this, it's a specialized bar graph. And then with histograms, there is no space between categories, between the bars. And this is the reason why. So since they're continuous, we want to see all the data aggregated together in a very, very clear, concise way to see the change overall in every category. So oopsies. So as an example, so histogram is really good with a timing category, like per year, this is the number of things. So the number of heart attacks per year. I don't know why that was the first one that came to mind, but that's pretty dark. But that's the type of thing. It's the Halloween spirit. So, given the table below, create a histogram for the number of crashes in Ohio each year. If you've ever been to Ohio, you know what I'm talking about. They have a bunch of bad roads. Partly due to the snow, I would assume, but just also crazy drivers. Then again, we also have crazy drivers here, so maybe it's just everywhere. Oh wait, no, you need to have the chart first before we can write the solution. So it has the year and then the number of crashes. Now, this isn't actual data, by the way. This is stuff I've made up.
I'm sorry. It's like really OCD. So we're drawing a chart and then we're gonna draw the graph.
Yes, we're gonna be given a chart and then we have to create the histogram from it. So I have 2017. There were 9,500. That's a lot of crashes, which is pretty accurate. 2018, there was I think 9,000. No, 2018 was a bad year. It was 10,000. Or no, 11,000. Let's go with 11,000. 2019, since halfway through 2019, we had a certain event that kind of made people stay inside. Things dropped a little bit, but since we were still able to be out and about during the first half of the year, 5,000. Then 2020 happened. And I mean, 2020 never happen, guys. That time period doesn't exist. And there were only 2,000. And then in 2021, it started to go up because we started to open up stuff again. So then it went back up to pre-COVID numbers. There we go. So our college president says, like, we are now back up to pre-COVID numbers in terms of our enrollment. Whatever, I don't care. Like, I don't really care. Like, I know it has to do with the budget, but whatever. And it's loud. In 2021, we had 7,000. There is a budget committee. I'm not on that one, but like we have a fall convocation and a spring convocation where we go to a president's address and he talks about how things are going. And so one of the things they're mentioning is like budget issues. It is.
It's not say that it is.
I mean,
it's not important. But
it is important, but many things that are important aren't very interesting.
it's not fun.
No, it's like a grading party. I think I've told you guys this class. No, in grad school, you have to go to a grading party for all your exams because there's like 700 to 800 people who take a course. So you all get together, all the TAs, you go down into the basement of a room where there's no light and no happiness at all. And you have to pick which problem you want to grade on the exam. And so if you're the last person to arrive, you have to pick the worst problem.
That sounds like torture.
So that's why you always wanted to have the room that was right above it instead of being in like the room that's like halfway across campus. So
Yeah.
to make sure that there's no happiness at all.
So you're just going to like a moldy basement to grade papers?
Exactly right. Exactly right. And they called it a grading party because it had pizza. It wasn't fun.
Pizza.
No, sometimes soda. Sometimes. But all right. Sorry for the distraction. So I'm gonna do this in increments of 2,000. But once again, it's your prerogative. If you want to do it every 1,000, you can do that. But I'm gonna make each tick mark 2,000.
Got 2,000, 4,000, 6,000, 8,000, 10,000, and 12,000. And that should encompass everybody because the highest value on my chart is 11,000. So, and then we'll just line them up by year. We'll start, so 17, 18. Is the comma after the year or is it before it? Do I write it like that or do I write it as comma 18?
No, it's before.
It's before, okay. That-
Yeah.
And 21. And so all we need to do is just make each little number line based on the total number of students. Or not students, the number of crashes. So 2017, 9,500. That's 9,000 would be directly in the middle of those things. So it's a little bit above that. Right about there. No, I did not want that. Right about there is fine. It's meant to be a 2018 was 11,000. So that's right in the middle there. 2019 was 5,000. So halfway between 6,000 and 4,000. Doesn't need to be perfect. Then 2,000 in 2020. And then 7,000, which is halfway between 8,000 and 6,000. That. So a histogram is very, very useful at looking for trends between categories that are all connected by something. So usually time is a very, very good measurement for like situation where you want to use a histogram. When you're comparing or things that are all continuous. So like age group, battery life going from like 0 to like number of, like I keep going to cell phones and batteries, I don't know why. But like 0 to 5 hour, 5 to 10, 10 to 15, 15 to 20, 20 to 25, whatever that is. Those are all continuous bins that are all connected to each other. So then two more little types of charts that we want to go over, and then we'll switch over to something a little more mathy, which is my type of thing. The next one we have are line graphs. My favorite type of graph, honestly. I like graphs that have I like graphs that look like functions, which we won't talk about in this, but they're used to analyze different categories over two metrics. Used to analyze different categories over two metrics. Where each line represents a different category. So an example I could think of would be measuring median household incomes each year in two different cities. Or states or whatever you want to do. So you have two metrics. You're measuring the years and the median household income. Those are the two metrics, and you're comparing two different categories, city 1 and city 2. A lot of times it's usually time is one of them. Like usually the horizontal or the x-axis is time. And then the vertical one is the other thing that's measured. But this is where each line represents a different category. So for example, use the following. Rainfall data. Of cities A and B, very, very distinct names, to create a line graph. So we're going to make a chart here. It's the year. And then city A rainfall. And then city B rainfall. So the years are 2000, 2001, 2002, 2003, and then 2004. Let's only do 4 or 5 measurements on the x-axis. For city A, and these are all in inches, so inches of rainfall per year. City A got 39, and then 42, and then 30, then 37, and then 39. City B got 20, then 23, then 50, and 27, and 27. So we're just tasked with creating a line graph for this situation. Though we could ask plenty of questions along with it, just similar to ones that we've been asking before, like what would be the difference in rainfall in the 2001 year between city A and city B, if given the chart and all that fun stuff. So let's go ahead and make that chart. So this. So let's go 2001, 2002, 2003, and 2004. And then the starting point is 2000. And let's just make it go up in increments of 10. I think that should be fine. So inches of rainfall on the vertical axis, time on the x-axis or the horizontal axis. And so we just plot the points. I'll let you draw the graph and then we'll go from there. All right. So city A, let's make city A in red. So in the year 2000, so right in here, it had 39, which is a little less than 40. So we'll plot it right there. In 2001, it had 42, so a little bit above 40. Then it went down to 30. In 2002, then 37, which is a little bit closer to there. And then 39 in 2004. So that's what, and then we just draw a line connecting them. I just want it to connect there. Fine, I'll draw. There you go. Now, one thing that I don't like about line graphs like this is that makes it seem like it was increasing and then decreasing like continuously. So there's a little bit of confusion there because like each, like, it's measuring the year on average, so it's not like in the start of January of 2000, of the year 2000, that it was at 39 and then it increased all the way up to 42 in January of 2000. It's just measuring each bit of data annually, but it still does give us kind of a good rundown. And then city, so I'm going to say that's city A. The red is city A, and then city B I'll do in blue. So it starts off at 20 and then 23, so a little bit more, then 50. So I must have had a good year that year, and then 27 and then 27. So right about there and right about there. And then we just draw lines connecting them. That's how you do it. And then, of course, as I said, like, we can ask plenty of questions. I just want to move on from this section, though. We need to get caught up. But you could ask, what was the difference in rainfall between city A and city B, which I need to still label city B. In the year 2002, when was the highest amount of rainfall, which would be 2002 for city B. Like, on average, who had more rainfall, you could look at it. And so on and so forth. Oh, excuse me. So there's plenty of stuff that we can do. But in the interest of time, we will move on to the last type of chart, unless there's any questions on this. Last type of chart, which is a pie chart. And much like, what was it, that one thing that we had to just talk about that bugged me? This is another one where it's part of the curriculum for whatever reason, so I have to teach it, though I think it's kind of a moot point. But oh yeah, the rule of 72. Yeah, much like that situation, it's something that I have to talk about, so that if you're ever on a stranded island, that you could create a pie chart by hand. So pie charts are typically used to show percentage differences. Between disjoint groups. Disjoint. Yeah. An example would be something like kids' favorite candy bars. Quite fitting because it's Halloween time. Used to show percentage differences between disjoint groups. I know the disjoint, I don't know which word is not making the most sense, but plenty of them are. So kids' favorite candy bars, like 25% of kids like Snickers bars the most. 50% like the GOAT, which is the 100-gram bar. Let's be real. Caramel chocolate and little Crispies.
I've met a lot of kids who just like Hershey bars.
Oh, crunch it. It's just a crunch bar, but better.
Yeah.
So like the 100 grams way better. Or those new sweet tart ropes, which are just fire, as the kids say, right? Is that what we say? We say they're fire. Okay. But yes, you can break them down into these different percentage categories. But that's the key thing about the pie chart, is it's usually almost always representing different percentage differences. So we're not like talking about like the previous example would not be an example where you want to really use a pie chart, because there's not really a percentage that we're looking at there. So kids' favorite candy bars, voting preferences, like Republican, Democrat, no party or whatever, no party affiliation. That would be a specific, like where we're looking at percentage of voters and things like that. That is where we want to use a pie chart. Now, the thing that's frustrating is how to create a pie chart by hand. This is the thing, like reading a pie chart, totally understandable why that would be a thing that we want to have questions on in this class. Totally get that, 100%. Being able to read a pie graph, great. Being able to construct a pie graph by yourself with your hand is an archaic thing that would never really be needed. Otherwise, I might just use Excel. But it's part of curriculum, so I guess I gotta teach it. I'm gonna see if I can actually just remove those problems and make them just like free credit if they can do it. I can't promise that it becomes free credit, but I will try to just remove those questions from being calculated, both on the if there's any on the homework or quiz or on the exam, the upcoming exam. I'll try to remove them. But in the meantime, how do we create it by hand? Since there are 360 degrees in a circle, for each group, we take its percentage of the whole data, of the total data, and multiply by 360 to get the number of degrees to each slice. So if 10 out of 20 people like the 100 grand bar as much, 10 out of 20, that's 50% of people. So 50% of 360 degrees gives us 180 degrees. So that's how we're using it. That's how it's created. That's how Excel does it. If you're curious, they figure out the total number of people tested in your category. Then they look at each different subcategory and figure out the percentage of the whole. And then they multiply that by 360 to get the exact right angles set up. But let's do an example so you can see how to do it. And hopefully I can make it like I'll be looking into it. I'm going to try and remove them. And if I can't, then I'll just like find out how many questions were on it and kind of boost everyone's grade on that homework assignment and quiz and stuff, because it's just not useful. But as an example of this, how to create it. In a survey of 50 students about their lunch sources, ten students brought home brought lunch. 5 bought a salad. Salad. 15 bought Dino Nuggies, the MVP. The MVP for any parents out there. 30 seconds, flip, 30 seconds, flip in the microwave. Done deal. So 15 bought Dino Nuggies and 20 bought the quintessential pizza. Create a pie chart. Anytime I hear another class, like watching a movie or something like that, I'm always curious what that class is about. I want to get to watch movies in my class. It'll be fun. Okay. So what we do is there's a total of 50 students. So we need to find the percentage of students in each subcategory and then multiply that number by 360 degrees to get the total number of degrees dedicated to it. So for the situation, 10 students, 10 home lunch. So that would be 10 divided by 50. That's 0.2 or 20%. Now that we have the percentage of students that ate a home lunch, now we need to figure out how many degrees that would correspond to. So 20% of 360 is 0.2 times 360, which is 72 degrees. So that piece of the pie chart should have 72 degrees in it. Five, we're a salad. So 5 divided by 50, that's 0.1 or 10%. Or I guess what I could even do to do it even faster, all I need to do is take, that's the percentage of students, 5 over 50, and then multiply that by 360, and you get 36 degrees. Then we do it for the, so that's salad. Then we got dino nuggies. So 15 dino nuggies. So 15 divided by 50 times 360 degrees. That should be 108 degrees. And last but not least, there were 20 pizza. So 20 divided by 50, which is going to be 40%. Times 360 is 144 degrees. So those are the amount of degrees for each section. Now we just got to create a chart for it. Got to create that pie chart for it. So we'll just draw a circle. As best as you can. And so if you don't know, each you can split this up into 4 quadrants. And each quadrant has 90 degrees. So usually we'll start, so this will be 0 degrees, this will be 90 degrees, then this will be 180 degrees. This will be 270 degrees, and then that's also 360 degrees when you get all the way back to the top. So it starts off at 0, and then it goes all the way down until you get to the end, and then it's 360 degrees once you finish it. And so you can split each one of those subsections up into intervals of 30 degrees if you want to, but we're just doing a rough estimate. But that's how it works. So each little side length, so north, south, east, and west, end up being 90 degrees added each time. So the first one was 72%. So we'll make a little chart. We'll go to the center, and 72, that's roughly about here. So that's going to be home lunch. And then it was 32 degrees, or sorry, 36 degrees for salad. So we were at 72, add 36, and we're at 108. So we should be here for the next slice. Right about there. And that's going to be salad. And then dino nuggies is 108. We're at 108, add another 108, or you can measure it roughly 108 is 216. So it's going to be from here to about I'd say right there. And then the last pie slice is pizza. And these are just rough estimates because we're hand drawing it. So we don't need to be super accurate, but that's kind of what it would look like. There's 144% in that pizza slice. Not a great, like, it's probably not 100% accurate if you were to bust out a protractor. Do you guys remember protractors?
Yeah.
It's a good time to be alive. Those and compasses. I have never used a compass ever, like, since like third grade. I know if I was probably in civil engineering, I might use it, but like, no, I haven't really used one ever since, but it was a fun time. So that's how we find each of those subsections. Now, what would be more important would be like interpreting the data. So like, what percentage of students like pizza to ate pizza or Dino Nuggies? So you add up those two percentages, which would usually be given. Or what percentage difference between pizza and salad, that type of thing. So that's how we could create one, and then we could ask plenty of questions on top of that. Is that okay? Any questions on that? If not, let's get to the more fun stuff, in my opinion, because I really like this topic, which is section 3.5. Oh, yeah, sure.
So you said in the whole pie graph there's 360 degrees, right? But when you add up 20% or 20, I'm sorry, 70, oh, that's what it is. Never mind.
You got it?
Yeah.
No worries. Standard deviation and the empirical, which is the 68, 95, 99.7 rule. The actual title of this section is just standard deviation and the empirical rule, but I find that the name of it, the empirical rule, is a really hard one to memorize, especially because of what it is. A lot of other textbooks will call it the 68, 95, 99.7 rule. And we'll talk about that soon, but we want to talk about standard deviation, one of the very, very important topics, especially if you decide to transfer to a college that does things based on a curve instead of a raw grading scale like we do. At least in my course. I know some like teachers at the CSN are kind of given their leeway to make their standard, like their grades however they want. But haven't really seen many people use a curve at CSN. But a curve can be great and can be wonderful. I think we've talked about it. So like, if everyone does really well in the course, like it's a 90%, then a 90% becomes like a B, and that's not good. But that's how I figured out what my grade would roughly be, is on standard deviations. So what is a standard deviation? Oh, wrong size font. Standard deviation. So the standard definition. The standard deviation of a data set is a measurement used to determine how much variance a data set has in relation to its mean average. The standard deviation is figuring out how much variance there is in comparison to the mean of the data set. Like how far apart are your data values from the mean itself? Are they all clustered together or are they very, very spread apart? Like, do we have a lot of people getting the same scores or do we have a lot of people getting a bunch of different scores? That is how we calculate standard deviation. So the formula is quite a doozy. The reason why it's only a doozy purely because we're talking about an arbitrary set of data values, x1 through xn. So there's x sub 1, x sub 2, x sub 3, x sub 4, all those n entries. And so the formula has to be written in general terms. So that's one of the things that always kind of scares people away from mathematics is that these formulas are very, very generic. But we're going to talk about how it comes to be. So a lot of people decide, a lot of statistics textbooks will use sigma or lowercase sigma, which kind of looks like a circle with a little hat on it. So I'm sure you've seen capital sigma, especially any of my Mega Man X friends out there, right? Mega Man X, final boss. Not that I know because I've never played Mega Man X. But that's a capital sigma, but a lowercase sigma kind of looks like that. Because I can't draw Greek letters very well. And it's equal to, and this is a decently large square root. In the denominator, it's just an n. But in the numerator, it is x sub 1 minus mu squared. That's a mu. A mu looks like an m with like that's what a mu is. It's hard to describe. Kind of looks like a U with a little extra lip on it at the beginning. So it's x sub 1 minus mu squared plus x sub 2 minus mu, a mu. It's
X what?
x sub 1. So subscript 1. And then plus dot 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 plus x sub n minus mu squared. We're going to talk about it. So I know it looks weird. I know it looks weird. And I'm going to explain everything here. I'm going to explain what this means. So x sub 1 minus mu squared plus x sub 2, the subscript 2, the second data value, all the way down to x sub n. So here in the formula, yes, plus dot 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 plus. So sigma equals the standard deviation, which we'll from now on write SD because standard deviation takes way too long to write. Mu is equal to the mean average of the data set. N equals the number of data entries. And then x sub 1 through x sub n. So x sub 1, comma, dot, 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 comma, x sub n is equal to the data entries. Let's write all that down and then we'll talk about the formula and how it all works out and how mathematics is very, very exclusive. It's a very exclusive study. And for a long time, it was very, very, I mean, in its conception, it's been quite a discriminatory subject, sadly. Slowly but surely it changes year after year, but there are still people in there that are problematic, that are trying to exclude people from being a part of it, which is frustrating. But either way.
Yeah, 100% that looks fair.
Yes. So one of the things that we have to understand is that we're talking, like mathematicians do this all the time, is the fact is, in order to create a generalized formula to approach any situation for a mean, for a data set, we have to use an arbitrary number, which mathematicians typically use n to mean an arbitrary whole number. So n could be 5, in which case there would be only 5 values in the data set. But how do you write down n entries, right? N is an unknown number, so you can't really write them all. So that's what that plus ... means. So we're just going to continue on this process of adding x sub 1 minus mu squared plus x sub 2 minus mu squared plus x sub 3 plus x sub 4 plus x sub 5, all the way until you get to the final entry of your data set. And so I want to talk about why this formula is the way it is. So as I said, the standard deviation is determining how much variance. Another way to think about that is the distance, measuring the distance between your data values and the mean average. So what would you do? So like looking at a number line, if this is your like average scores, right? This is your mean average. Let's say it's a 77. And here are your 3 scores. One person has a 76. One person has a 71, and this other person has a 79, right? So don't worry about it too much. Where 77 is the mean. This person has a distance of 2 between them, right? And how did I do that? I took 79 minus 77, right? 79 minus 77, that's where I got 2. Here, there's a distance of 1. Now, I got that by doing 77 minus 76, but if we wanted to do it generalized, I'd say it's 7, like you always put the first number first, but then that ends up being a problem. So the first thought in trying to figure out the averages of these things would be, okay, we'll take the distance of the first set. So x1 minus mu plus x sub 2 minus mu plus plus x sub n minus mu, and we'll divide that by the total number of data values. That would give us the average, but the problem is that some of if I wanted to know an actual distance from the mean, some of these numbers would be negative. And we don't want to really have a negative distance. That doesn't make much sense. So what we do as mathematicians to kind of bypass that is we square it. We raise it to the second power, because if you raise anything to the second power, it becomes positive. -1 squared is +1. -10 squared, +100. So anything that's positive will just get squared and stay positive, but anything that was going to be a negative distance now gets squared. But that's going to be what we call the square distance between the data value and its mean average. So what do we do to kind of counteract that? We square root it, because remember, the square root and the square kind of undo each other. So it's the square average, or like square distance between the data value and the average of those things, and then square rooted. That's where the formula comes from. So it's talking about trying to find the distances between each data value and the mean, and then dividing it by the total amount. That's how the standard deviation came to be. Because and that's basically kind of the argument that came about on how to create this formula. Was someone said, well, let's just do x sub 1 minus mu plus x sub 2 minus mu plus x sub 3 minus mu, all divide that by n. But then ended up being a problem, as I said, because some of those distances would become negative. Unless all the data was to the right of the mean, which can't happen, because then the mean would be in between those values. So that becomes the problem. Yes.
What's the third? What's that x? What is x of?
The last one?
Yes.
That'd be x sub n.
Okay.
So yeah, x sub n. So like the last data entry. This was mainly meant to try and prove what's going on here and why the formula is the way it is. So I'm not actually I'm not going to test you on how to create the standard deviation, and I don't expect you to have that formula memorized. It's quite a doozy. It's a cool formula. It's like, I hope you can respect how it was created. Because I didn't realize, because I'm not a statistician. I don't really study statistics. Because I don't really like it. But I didn't start realizing that until like like in my grad school when I had to calculate it for my own classes, what it really meant. I just knew how to find it because my like I didn't understand what it meant. And it took until grad school to figure that out. So by the way, let's go ahead and actually use it and show you that it's not as scary of a formula as you think it is. So example, once you see it in practice, it's like, oh, okay, I see what's going on here. So calculate the SD, the standard deviation of the set 55, 42, 77, 63, 63, and 71. And the round to the hundredths. And so if your school, if you decide to transfer to a different school and they use a curving system, if you want to figure out like the general rule of thumb is anything above 2 standard deviations is pretty much an A. So you usually want to try and be within 1 standard deviation above if you can. Now, within 1 standard deviation usually means you're in the B to A range. But anyways, so solution for this, because the standard deviation relies on the mean average, we need to first find the mean. Which we call mu in this case. That'll be the mean, and so that's going to be adding up all the numbers. So 55 plus 42 plus 77 plus 63 plus 63 plus 71, all divided by 6, because there's 6 data entries. So that's going to be 61.83 when you plug it into your calculator, just to save on time. You find the mean of the data set because that's how you make the standard deviation. So when you're doing this, it becomes a little bit long of a process. So make sure you start your sigma over on the left over here. Make sure you have a full page to write it, because it's going to require a lot of space. No, I did not mean to make that. So I'm going to see how much space I need. But okay, so we're going to do the first data value, 55, minus our mean, 61.83 squared, plus our second data value, 42, minus 61.83 squared, plus our third data entry, 77, minus 61.83 squared, plus our next data entry, 63 minus 61.83 squared, plus 63 minus 61.83 squared, plus, and I did not give myself enough space. I suspected as much. Scrunch them back more. Sorry, guys. That should give me enough room. There we go. And then last one, plus 71 minus 68.3 or 61.3, excuse me. 61.83 squared, and then the end of the square root, and then all divided by 6. My recommendation, unless you've got a good calculator for it, is to compute the numerator first and then divide it by 6 and then take the square root. So using the answer button. If you do it correctly, if you calculate the numerator first, you should end up getting the square root of 756.8334 or so. Divide that by 6, and if you plug that into your calculator, you'll get 11.2311575, which is approximately 11.23 when we round to 200, to the hundredths.
So just add it all together and square it first.
So no, each one is squared separately. So that actually brings up a very, very classic confusion, is that each thing squared is not the same thing as adding up all the differences and squaring that. So we have to take each one, square it, and then add it to the next one.
Then you just divide.
That's, yes. And then take the square root, that's correct. Do you see how it, like, does that make a lot more sense now you see it in action? It is just find the mean, take the difference and square them, add them all together, and then divide by the total number of numbers, and then take the square root of that. So standard deviation of 11.3. So since the mean is a 61, if you scored a 74, you're one standard deviation above, you probably got a B or a B plus. So typically speaking. Now I wanted to make an observation about the standard deviation.
That comparable with something 756.8334.
Yes. If we changed, so this is the observation, if we changed the last data entry to a 99, i.e., we have the data set 55, 42, 77, 63, 63, and then a 99. I wanted to so looking back at the previous set of data values, so it was 55, 42, 77, 63, 63, 71. All of those are pretty close together, right? They're pretty decently close. Not great, but in total, there's a variance of 35. Whereas now there's a difference of 40 or 57. There's a larger variance of data values. So if we change the last data entry into a 99, then the standard deviation, then SD, is equal to 19.61. Granted, so I don't want to go through the calculation of it, but this would be something that you'd want to do on your own time. Is now the last data value, all the things change because now the mean is different, because the mean will be using a 99 instead of a 71 for the last data entry. And then you need to calculate the standard deviation of that. But if you do go through that and calculate it, you'll get 19.61, which is a larger standard deviation. So fact, as a result of this, the larger the variance in data values, the larger the standard deviation. So if you've got a very, very small standard deviation, if you've got a 1 for your standard deviation, that means that there was not much variance between the data values. So that's what usually happened in our courses at UW, is the standard deviation was 2.5. So getting a 45 when the average is a 40 was a big deal. Because that would be if standard deviation was 2, you're 2 standard deviations above with the 45. So that is an important fact. And that goes in reverse as well. The smaller the variance, the smaller the standard deviation. Let's do one more. One that doesn't necessarily have a nice, or an integer or a decimal average, so that it ends up being a little bit smaller. Let's do one more example of a standard deviation. Example. Find the SD. Find SD for the data set is 30, 30, 31, 35, and 39. So these numbers are pretty dang close together. There's only a difference of 9 total. So that would be like, if you want to like get more practice, definitely go back over tonight, maybe when you're hanging out with your besties or your bros and your bro-ristas. Go ahead and do that problem with them. I think that'd be a very, very good bonding experience with your teammates. I think they'd have a great time with that. Probably why I don't have friends, but neither here nor there. Standard deviation, we need the mean. Yay for self-depreciation here, humor. 30 plus 30 plus 31 plus 35 plus 39, all divided by, there are 5 numbers, right? Yes. And so if you plug that in, you should get 33. So the mean mu, I guess this is our second mu, or mu2. Not that I've ever played Pokemon, but I heard that that's a Pokemon name. But anyways, so sigma is going to be the square root of all the data values minus the mean, and then square that thing. So 30 minus 33 squared. Plus another 30 minus 33 squared. Plus 31 minus 33 squared. Plus 35 minus 33 squared. Plus 39 minus 33 squared. All divided by 5. Write that down. And then, so you should get, if you plug that into your calculator correctly, you should get 62 divided by 5, which is approximately 3.52 when we round. Which makes sense. The variance in the data was not as large as the previous 2 problems. So we should get a smaller standard deviation. Any questions on that?
So,
Yeah, the formula, when you see the formula, it ends up being a lot more difficult than in practice. I mean, there's plenty of examples of that in mathematics. And it just takes time to get comfortable with that notation. So for example, in Math 126, we talk about polynomials, and we have to talk about a general polynomial. Like we write P of X, and then we write a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub 0. And it looks really, really complicated to students at first, but it's just meant to be a generic polynomial. So most of the time we see something being like 6x squared plus 3x minus 9, something like that. But that's just how we could write it. That's how we write it if we were having to write a general polynomial. So it's just a common thing that mathematicians do. And the more you study mathematics, the more comfortable you get with that notation. It is a different language. Mathematics is a different language at times. The universal language. So that's how you calculate standard deviation. Now, what we are interested in, and so we won't be able to finish it today, but that's okay, is the normal a normal curve. A normal curve / distribution. I like the terminology distribution more, but you can, some people also call it a normal curve. And what it is, so definition,
a set of data values has a normal distribution if the data values are symmetrically dispersed with a majority of the values clustered around the mean of the data set. That's what a normal distribution is. So you want all your data values to kind of be symmetrically set up. So we're seeing like if you have one outlier, one large outlier on the right, you should have one large outlier on the left of your data set. And that the most of them should appear near the average, near the mean average. So in a picture, which is worth 1,000 words, what you end up with is you have this chart, this graph. So on the x-axis or the horizontal axis, you have the data value measurements. And then on the vertical axis or the y-axis, you have the frequency. And as a reminder, the frequency is the number of times the data value occurs. And so what a normal distribution would look like, once you've written that, it should look something like this. And so right in the middle here, at the highest peak, let me use a different color, is the mean. That's right. That's going to be mu. That's the mean. And we called, this is called a Bell/normal curve. So the frequency, I'll let you guys finish this, and then we'll kind of talk about it. Yeah, we got minutes. Yeah, we'll finish up this, and then we'll deal with the empirical rule tomorrow or on Wednesday. But so basically, the frequency is the number of times that it occurs. So in your data set, it would look something like 37, 38, 39, 40, 40, 40, 40, 40, 41, like about a bunch of times. And then like the mean is, let's say, 44, and then it'd be a bunch on the other sides. And so you get this situation where on both sides of the mean, you have a lot of data values, and then it starts to taper off on both sides. So these occur quite often in nature when you have a lot of data values. We can't really see a bell curve if I only give you 5 data values, right? Like they're not really going to happen. But when you're studying things that happen very like with large quantities, so another like an example we had talked about last time would be birth weight.
those things tend to be normally distributed. Birth height, head size, standard test scores, those are also usually normally distributed because there's just so many of them. So that's how we find standard like normal curves. And it's very, very useful to have a normal curve, which we'll study in a second, which has to do with what we call the empirical rule. But we'll cover that more in detail on Wednesday. All right. So that'll be it for today. If you have any questions, feel free to email me. Otherwise, you guys have a great rest of your day, and I'll see you guys on Wednesday. What? Happy Halloween. Absolutely. You guys have a great Halloween. Make sure don't make any don't do anything stupid. Don't break anybody's jack-o'-lanterns. Don't do any of that stuff. True. Check. Yes.
Are you gonna do the county tax?